Hello everyone, today let's take a look at some combinatorics with some inclusion-exclusion. We're going to be looking at QP 103 here. So basically we have the Evarts family with 3 sons and 3 daughters. So in how many distinct ways can the 6 children be seated in a row of 6 chairs so that neither all 3 boys nor all 3 girls are seated consecutively? So for instance, if we have our 6 chairs right here, well then this would be an invalid seating because we have all 3 girls right next to each other. This would be another invalid seating because again we have all 3 boys next to each other and all 3 girls next to each other, and we want neither of these to happen. So to solve this, we could go through every single iteration where they're not seated consecutively and then calculate the number of combinations for each of those, but that's going to involve a lot of cases. So if we use inclusion-exclusion, it's going to make our lives a lot easier. So to solve this, let's just calculate the total number of ways to seat the 6 children, and then we can just subtract off the cases where there are either 3 girls or 3 boys seated consecutively. So we have 6 distinct children here. There's going to be 6 choices for our first seat, 5 for our second, etc. You know the drill. The total number of ways to seat these children is going to be 6 factorial. Now we need to subtract off our invalid cases where all 3 girls or all 3 boys are seated consecutively, denoted by B and G. Those will be our set names. So right here we have the set where all 3 boys are seated consecutively, and over here we have the set where all 3 girls are seated consecutively, and there is some overlap because we could have them both happen at the same time. So I'll say this is B here and this is G here. And again, we need to subtract off the cases where either of them are true. So we're going to take the union of these 2 sets and we're going to subtract them from our total to get our final answer. So all we have to calculate is basically the magnitude of the union between the set B and G. And we know how to do this using inclusion-exclusion. It's just going to be equal to the magnitude of B plus the magnitude of G and then minus their intersection because we would have overcounted it, right? So B intersection G here. So first let's calculate the number of combos where all 3 boys are seated consecutively. So that would look like something up here where we have triple B in one block, and then we have our 3 girls over here. So now when we block off all of the boys together, well now it's like we have 4 distinct elements that we can permute in 4 factorial ways here. So we're gonna have 4 factorial, and then we need to account for the number of permutations within this block itself. So within this block over here, I have 3 distinct boys, right? 1, 2, and 3, which I can permute in 3 factorial ways. So for every single one of the 4 factorial permutations of this block with the 3 girls, we're going to have 3 factorial permutations of the 3 boys inside of it. So again, the 4 factorial is to account for the different permutations of the block of 3 boys. So for instance, this one should be counted differently than this one, and then we multiply by 3 factorial because for each one of those, we could have 3 factorial permutations within this block itself. So that's the magnitude of B. Now let's calculate the magnitude of G, which is the number of combinations where all 3 girls are seated consecutively. So we can do this one in exactly the same way. We block off our 3 girls so that we're only counting the cases where all 3 girls are seated consecutively. And then we have 4 basically unique items up here that we can permute in 4 factorial ways. For instance, this one will be counted differently than this one here. And then for each one of these permutations up here, we have within this block 3 factorial permutations of where the girls can go, right? So for instance, this should be counted differently than this, and this should be counted differently from this one over here, obviously. So again, same story for G. This is going to be 3 factorial times 4 factorial, but now we need to account for their overlap, which we would have counted twice in these calculations over here. And again, that's just because when we calculate the magnitude of B, we're counting everything in this green area. When we calculate the magnitude of G, it's going to be everything here. So look, we're counting the intersection twice, so we need to subtract it once. And the combos that got overcounted are, for instance, when I was calculating the magnitude of G, this permutation right here where all 3 G's were on the end, well, notice that all 3 boys were also on the other end, right? So this would have gotten counted in the boy arrangement as well, but we only want to count this one time. So to get the number of overcounts, we can just block off all the boys as well. And then we have 2 factorial ways to permute these 2 distinct elements where all the boys are on the right or they're all on the left, right? And then within each of these blocks, I can permute all their elements in 3 factorial ways. So I need to subtract off the 2 ways of arranging these blocks. And for each of these, I have 3 factorial ways to permute these. So let's say 3 factorial and 3 factorial ways to permute the boys. So again, another 3 factorial. So it's going to be 2 times 3 factorial squared right here. So this number right here is going to give me the magnitude of intersection between the sets B and G. So it's just going to be all the combos where either all 3 boys are seated consecutively or all 3 girls are seated consecutively. And then we can just subtract this from our total once we calculate it. So to calculate it, I know 3 factorial is 6 and 4 factorial is 24. 6 times 24 is 144. And then we have that again over here. So I'll add 144. And then we have 2 times 3 factorial squared, which is going to be 2 times 36, which is going to give us 72. So that ends up equaling 216 combos where either all 3 boys are seated consecutively or all 3 girls are seated consecutively. And now we just need to subtract that from our total to get the number of combos where neither of these are true. So we take 6 factorial, which is going to be 720, and we just subtract off 216, and that'll give us 504.